Hello again everybody. In the previous lecture we provided a pathway for handling molecules using Schrodinger's wave equation. We provided a pathway for handling molecules starting with the solutions of the individual constituent atoms. In fact, we attempted to provide an approximate solution for the H2 plus, the hydrogen molecular ion problem, which contains two protons and one electron. So just like in the case of atoms, we have the electronic structure given by the 1s, 2s, 2p, etc. energy levels. In the case of molecular systems, the electronic structure goes in terms of sigma, pi, delta, and so forth orbitals. And we will talk more about that today. Let us first very quickly draw the electronic structure that we ended up with towards the end of the last lecture for the H2 plus system, and we're going to build on that. We're going to move on to H2, the neutral H2, and then other homonuclear diatomic molecules and so forth, and we'll finally end up with solids. So there it is. So here is the electronic structure we drew towards the end of the previous lecture. On either sides of this figure, you see the 1s orbitals of the hydrogen atom that will eventually make up our H2 plus system, or even the neutral H2 system. So those are the atomic orbitals, the 1s orbitals. They combine together in a bonding manner to create the 1 sigma 1s orbital that is lower in energy compared to the atomic 1s orbitals, and we also have the antibonding combination of the two 1s atomic orbitals, which we are labeling as 1 sigma 1s star, which is of course higher in energy compared to the two atomic 1s orbitals. So while the 1s, 2s, 2p and so forth orbitals are atomic orbitals, the 1 sigma 1s, 1 sigma 1s star and so forth, we will end up with more eventually. Those are called molecular orbitals. So in the case of our molecular systems, those are the energy levels we should focus on, and those are the energy levels that we should start filling up. In the case of the H2 plus system, we have only one electron, and so that one electron will actually sit in our 1 sigma 1s, the bonding orbital. So we're going to use this notation going forward. Just like in the case of a hydrogen atom, we say that the one electron is sitting in the 1s level, and we use the notation 1s1. And then moving on to helium, we say its electronic configuration is 1s2, meaning that two electrons are sitting in the 1s level, and so forth. We are going to use a similar type of notation for molecular systems as well. So extending that analogy further, we would say that for a neutral H2 molecule, which has now two electrons, the electronic structure, the molecular orbital electronic structure is going to be 1 sigma 2. And likewise, as you move to slightly bigger atoms, let's go on to helium, right? Helium 2 plus and neutral helium 2, we would get the following types of electronic structure. So here are the electronic configurations for a bunch of molecules, right? So note that I have, just for simplicity, suppressed the subscript 1s, because in all of these sigmas have a subscript 1s, but just to avoid clutter, I've just suppressed that. But it's understood, at least in the case of these systems, that there is a 1s subscript, indicating that the origins of our sigma orbitals, sigma molecular orbitals, sigma and sigma star molecular orbitals are really the atomic 1s energy levels. Okay, so for H2 plus, we have one electron only, and so that is going to sit in the bonding 1 sigma level. So its electronic configuration is 1 sigma 1. For H2, there are two electrons. You place two electrons in our bonding level, so its electronic configuration is going to be 1 sigma 2. Moving on to helium 2 plus, meaning you have two helium atoms forming a molecule, and you're pulling out one electron from that molecular system, making it singly positively charged. So this helium 2 plus system will have 3 electrons in the system. So 2 will go to the bonding sigma orbital, and the other third electron will go to the antibonding sigma star level, and so its electronic configuration is going to be given by 1 sigma 2, 1 sigma star 1, and finally going on to the neutral helium dimer, this system over here, which clearly has 4 electrons, so its electronic configuration is going to be 1 sigma 2, 1 sigma star 2. Okay, so at this point let me make a very interesting, useful and revealing observation. Recall that when we discussed the nature of the bonding and the antibonding orbitals earlier, I noted that the bonding orbitals have the feature that electron density gets enhanced at the bond center, and conversely, in the case of antibonding orbitals, there is a depletion of electron density at the bond center. In fact, there is a node in the wave function at the bond center, implying that the electron density at the bond center is actually 0. Thus, when electrons are placed in the bonding molecular orbitals, the molecule gets stabilized, and in contrast, when electrons are placed in the antibonding orbitals, the molecule gets destabilized. This is what we expect. In fact, these notions are the reasons why we believe that the H2 plus molecular ion is stable in the first place, because it has one electron, and that one electron at ground state resides in the bonding 1 sigma 1s orbital. And extending that argument further, in the case of the H2 neutral hydrogen molecule system, you have 2 electrons, and you would at ground state place those 2 electrons, both the electrons in the 1 sigma 1s bonding orbital, and so you expect the H2 system to be even more stable than the H2 plus molecular ion. In fact, that is the case. So what I'm going to do right now is to very quickly make a plot of the potential energy or the total energy of the H2 plus and the H2 systems as a function of the interatomic bond distance r. So there it is. This is the total energy of our H2 plus system as a function of the bond length r, the interproton distance r. And this is something we touched upon at the very end of the previous lecture. So the total energy has a minimum, and the minimum occurs at a bond distance of 1.08 angstrom, and the bond energy corresponding to that distance is 2.7 eV, meaning that's the energy we need to supply to break up our H2 plus ion. And likewise, here is the total energy as a function of the inter-proton bond distance for H2, for the neutral H2 system, which also, of course, has a minimum in the energy, and the minimum occurs at 0.76 angstrom, and the bond energy corresponding to this molecular system is 4.7 eV, meaning you need to supply 4.7 eV to break up our H2 molecule into 2 isolated hydrogen atoms. So a couple of things are immediately obvious. First of all, the equilibrium bond distance for H2 is smaller than that of H2 plus, and secondly, the bond energy of H2 is larger than that of H2 plus. Both are stable systems, but clearly H2 is more stable than H2 plus, as it has a larger bond energy. Another thing which may not be immediately obvious here is the curvature of the two curves at the minimum indicates that the H2 molecule is actually stiffer. Larger the curvature at the minimum, the stronger the spring constant, the larger the spring constant associated with the vibrations. And hence we say that the molecule is stiffer. It will display a higher vibrational frequency at equilibrium. So the picture that we have arrived at is consistent with the notion that I proposed earlier, that if you have more number of electrons in the bonding orbital, then your system will be more stable. So H2 has 2 electrons in the bonding orbital as opposed to H2 plus. As a result, H2 is a more stable system. It has a larger bond energy compared to H2 plus. It also has a shorter bond compared to H2 plus, and it is also stiffer. What about the other systems, right? What about He2 plus? It has 2 electrons in the bonding orbital and 1 in the antibonding orbital. And moving on to He2, the helium dimer, the neutral helium dimer, it has 2 electrons in the bonding orbital and 2 in the antibonding orbital. Based on the discussion arguments that we have made so far, we can safely conclude that the helium dimer is going to be not very stable, because it has 2 electrons in the bonding orbital, which provides some stability, which is pretty much offset by the destabilization factor due to 2 electrons in the antibonding orbital. So helium 2 is not expected to be stable, and in fact experimentally helium 2 has not been observed. Helium 2 plus is an interesting situation. Experimentally, helium 2 plus systems, ions have indeed been observed, and the rationale for that is you have 2 electrons in the bonding orbital, one sigma 1s orbital, but you have only 1 in the antibonding sigma star level, and so the bonding influence of the 2 electrons in the bonding orbital outweighs that of the antibonding electron in the antibonding orbital, and so there is a net stabilization, and indeed helium 2 plus, as I just mentioned, is observed experimentally. The notions that we have introduced so far may be used to define how many bonds, determine how many bonds a molecular system has. In fact, that's exactly what we are going to do right now, and I'm going to provide a definition for the number of bonds a system can display. So this is the definition we are going to use. The number of bonds displayed by a system is actually equal to the net number of electrons in bonding orbitals divided by 2. Note that this definition immediately implies that a neutral H2 molecule has 1 bond. Why? Because it has 2 electrons in the bonding orbital. So 2 divided by 2 gives you 1. So a neutral H2 has 1 bond, a single bond. Of course, we could use the same definition to go back to our 4 molecular systems that we considered earlier and identify the number of bonds that we expect each of those systems to display. So there it is. So according to our definition, H2 plus has half a bond because it has just 1 electron total, and that 1 electron is in the bonding orbital, so it's 1 divided by 2. So H2 plus displays half a bond. H2, the neutral H2 molecule, as we just discussed, displays 1 bond. Helium 2 plus system has a total of 3 electrons, but 2 of them are in the bonding orbital, and the third one is in the antibonding orbital. So the net number of electrons in bonding orbital is 2 minus 1. That's just 1 electron divided by 2 gives us half a bond. So He2 plus is expected to be about as stable as H2 plus. And when we move on to He2, the neutral helium dimer, as we already discussed earlier, it has a total of 4 electrons, but 2 of them are in the bonding and 2 in the antibonding orbital. So a net number of electrons in bonding orbital is 0. So it has to display 0 bonds, as is reality. So these are indeed very powerful notions, and we will remember them as we move forward into this lecture and future lectures. And in addition to the notion of the definition of the bond, we also would like to remember the 3S rule, which, as I a little while ago described, indicates that shorter bonds are stronger and stiffer. And so there is the 3S rule, indicating that the more number of electrons you have, the more number of net bonding electrons you have, that system will be stronger and will display shorter bonds and stiffer bonds. The same argument, in fact, interestingly, can be extended to solids as well, meaning that a more stable solid will display uh, shorter lattice parameters and larger cohesive energies and larger bulk modulus. And we will encounter that as well when we move on to solid state systems. Okay, so what we are going to do now is to extend this picture, this electronic structure, molecular orbital picture, to other orbitals, right? So we have drawn this for the specific case of the 1s atomic orbitals combining to form bonding and antibonding combinations, molecular orbitals. Um, Now we are going to extend that to include other higher lying orbitals as well, and this will allow us to handle larger atoms. So that's the next step. Okay, so here is our extended picture that involves the higher lying atomic orbitals 2s and 2p. The atomic orbitals, just like before, are shown on the left and the right corresponding to the two atoms that would combine together to form our molecule, and the molecular orbitals are shown right in the middle. Note, of course, that we do have the 1s orbital lying below the 2s level. It's not shown here, partly because we have discussed that before, and also to provide us some additional space and for clarity. So the two 1s atomic orbitals would, of course, combine together to form the bonding and the antibonding combinations, the molecular orbitals 1 sigma 1s and 1 sigma 1s star, and those molecular orbitals are, of course, lying below the molecular orbitals that you are seeing in this slide. Okay, so let's take a look at our new higher energy, higher lying molecular orbitals. So the 2s atomic orbitals combine in a bonding and antibonding fashion, just like our 1s levels did. And so the 2s levels provide us with two molecular orbitals, 2 sigma 2s, which is a bonding combination, and 2 sigma 2s star, the antibonding combination. And likewise, when we go up to the 2p levels, note that we have three 2p levels, px, py, and pz. And we assume that our molecular axis is along the z-axis, and note that we'll have our pz, the 2pz atomic orbital oriented along the molecular axis in that case. And as a result, our 2pz atomic orbital will combine in a bonding and an antibonding fashion to create our 3 sigma 2p and 3 sigma star 2p levels. There is a reason why we are calling this a sigma. We'll get to that in a short while when we talk about the other two 2p levels, which are the 2px and the 2py. These two 2p atomic orbitals, namely the 2px and the 2py, are oriented perpendicular to the bond axis, which is the z-axis. And because they are oriented perpendicular and they are p-type orbitals, it turns out that their bonding and antibonding combinations will be labeled as pi. And that's what you're seeing over here. So the 1 pi x and 1 pi y correspond to the bonding combination of the 2px and the 2py atomic orbitals, and the 1 pi x star and 1 pi y star are correspondingly the antibonding combinations of those two 2p orbitals. Now, the reason again as to why some of the p combinations are called as sigma and the others are called as pi can be understood simply based on symmetry. And I'm going to draw a couple of pictures to highlight the fact that there are two distinctly different combinations of the p orbitals. Okay, so first let's discuss this 3 sigma 2pz combination. This is the bonding combination of the two 2pz orbitals, and I've shown a picture of how the two 2pz atomic orbitals come together. So the shaded region indicates the positive lobe of the 2p function, and of course this unshaded region indicates the negative lobe, and again this is the positive lobe and this is the negative lobe for the other 2pz atomic orbital coming from the second atom. And when these two 2pz orbitals come together in this manner, you see that the positive lobes team up to create an accumulation of electronic charge density in this region, which is the bond center, which is why it is called the bonding combination. One could also visualize the situation in terms of the actual values of the wave function as you go from one atom to the other. And let me very briefly, very quickly picture. So there it is. You see what is plotted over here is really the value of the wave function as a function of position, and these two black spots indicate the actual location of the two atoms, the two nuclei. And what you see here is a pictorial representation. It's something like a contour plot of the wave function in three-dimensional space, and what you're seeing here is really a one-dimensional plot. The value of the wave function as you go through the molecular system in that manner, right? So these are the two positions of the two nuclei, the two atoms, and the wave function displays a negative value here. It's positive, and then because it gets added on to the corresponding positive part of the wave function of the other atom, you get an accumulation of charge density at the bond center, and of course on the other side it's negative, corresponding to this particular lobe. So this is the situation of the with respect to the bonding combination of the two 2pz orbitals. Now all the other cases can actually be understood in a similar manner. Let's very quickly plot how the antibonding combination of the two 2pz orbitals is going to look. Okay, so there it is. So here is our picturization of the antibonding combination of the two 2pz atomic orbitals. Here is one 2pz, here is the other, and in contrast to this situation over here, you see I have drawn the lobes, I've chosen the signs of the lobes such that you have a positive part of the wave function over here, and the negative part of the wave function is over there. And here is the one-dimensional plot of the wave function along the bond length. And you can see that because this is an anti-bonding combination, meaning you have a positive lobe here and a negative lobe there, you get a node. You get a node at the bond center, meaning there is a depletion of electron density. And note that the electron density is the modulo square of the wave function. So anyway, so there is a depletion of electron density at the bond center, which of course would destabilize the molecule. And this is why it's called the anti-bonding combination. Now let's move on to the px and the py atomic orbitals and their combinations to create the pi molecular orbitals. And here is a picturization of the two py atomic orbitals. You have again two of them coming from the two different atoms. They combine together in this manner to create the bonding combination, which we call as 1 pi y. And again, this is the positive lobe, this is the negative lobe of the wave function, and you have the positive and the negative lobes over there for the second atomic orbital, and you see the positive and the positive match up. They reinforce each other, creating an accumulation of charge at the bond center. Likewise, the negative and the negative reinforce each other and also create an accumulation. So at the bond center, the py orbitals combine together in a bonding fashion in this manner and lead to accumulation of charge density at the bond center. And now let's move on to the antibonding combination. There it is, our antibonding combination. The only difference between this combination here and this molecular orbital is that the lobes of different signs are matched up in the antibonding combination, whereas lobes of the same type are matched up in the bonding combination. So you see you have the positive lobe here coming together with the negative lobe there. Of course, when these two lobes come together, you are going to have a node. Your wave function is going to go through a zero at the bond center. And likewise, you have the negative lobe here and the positive lobe here, and at this point at the bond center you're going to have a node, and the wave function is going to go through a 0, meaning you have depletion of electron density at the bond center, leading to destabilization. Okay, so now we are going to address the fact as to why we called some of the p combinations as sigma and the others as pi. One thing I want to note here is that in the sigma combination, which are these, right, this one here and that one there, there is no nodal plane along the bond axis, right, along this axis, along this axis. You cannot say that the wave function is 0 throughout. Same thing over here along this axis. You cannot say that the wave function is 0, although there is a point here where the wave function is 0. But you cannot say that there is a plane over there where the wave function is 0 throughout. On the other hand, for the pi combinations, which are these two, you see that along the bond axis you can create a plane, and if you visualize, you will see that the wave function is actually 0 in that entire plane. And for this case, for this example, that is the case, and for this antibonding example also, that is the case. So there is exactly one nodal plane along the bond axis in the case of the pi combinations. So sigma orbitals, the sigma labeling is used whenever the wave function has no nodal plane along the bond axis. The pi label is used when there is exactly one nodal plane along the bond axis. And extending this further, delta, that is the next one, right? The delta type of molecular orbitals will have two nodal planes along the bond axis, and so forth. So this is the reason for the nomenclature sigma, delta, etc. Okay, so let me make one final observation before we move on to the next segment, and that is this notion of conservation of states or orbitals. You see, if you have n atoms, each atom supplying m orbitals to the molecule, then we will have a total of n times m orbitals in the molecule. For example, let us take this picture that we have in front of us for a second. We assume that our system, our atoms provide 1s, 2s, and 3 2p orbitals, right? So that's a total of 5 atomic orbitals that are supplied by our atoms. So you have 2 atoms, right? So we are considering diatomic molecules, so you have 2 atoms. So that's a total of 10 orbitals that are being supplied by the atoms. And what I'm saying is that when you have the molecule, you will also have a total of 10 molecular orbitals. That's all. And you can very simply verify that. You see, let's start from the top. 1, 2, 3, 4, 5, 6, 7, 8, and of course the 2 more that come from the 1s orbitals. The point is that the number of states or orbitals is conserved. Okay, so now let us use this molecular orbital diagram to figure out the electronic configurations of other bigger diatomic molecules. We have considered 2 diatomic molecules so far, the H2 system and the He2 system. Now let us now graduate to larger atoms, and let's figure out their electronic configurations. Okay, so we are going to create a table. We are going to consider 5 homonuclear diatomic molecules. Note that when we say homonuclear diatomic molecules, we mean that the 2 atoms that our molecule is made out of are the same type of atoms, right? So H2 and He2 that we considered earlier are 2 examples of homonuclear diatomic molecules. Now here we are going to consider 5 more such homonuclear diatomic molecules made out of larger atoms. Boron 2, carbon 2, the nitrogen dimer, oxygen dimer, F2. Right? And for each of these examples, for each of these 5 dimers, we're going to write down the electronic configuration. We're going to figure out the electronic configuration. That's easy to do, right? Because for each case, for each dimer, we know the total number of electrons that we have, and we also have the electronic configuration diagram, the molecular orbital diagram which we just created. So we start occupying the molecular orbital levels starting from lowest energy till we run out of electrons, right? So we're going to figure out the electronic configuration for each of these 5 dimers, and then we'll figure out what the net number of bonding electrons is. That's the total number of bonding electrons, total number of electrons in the bonding orbitals minus total number of electrons in antibonding orbitals. That's the net number of bonding electrons. And then we will look up the bond energy for each of those 5 cases and the bond length, and see if our 3s rule works for these systems. So that's the goal. Okay, so now let's move on to B2. Boron has an atomic number of 5, meaning it has 5 electrons. So the B2 dimer has 10 electrons. So we need to go back to our molecular orbital diagram to figure out how to occupy these levels with our 10 electrons. So okay, out of the 10 electrons, 4 of them will go to the 1 sigma 1s and 1 sigma 1s star level. So 4 are gone. So you got 6 more left. So so we'll put 2 here, 2 here, and we need to put 2 in these 2 levels. Now, although each of these levels can occupy 2 electrons, each of these pi levels can occupy 2 electrons, we have 2 of those and we have 2 electrons, and since the 2 pi levels are of the same energy, they are degenerate, you need to put 1 electron in this level and the second electron, the last electron in that level. So that would be our electronic configuration for the boron dimer. So there it is. That is the electronic configuration for the B2 dimer. So the stuff in square brackets will repeat for all of the subsequent cases, and that is why I put a square brackets around that. So I'm not going to write down everything explicitly, just to save some space and time. I've also omitted the subscripts for each of the molecular orbital labels, right? So instead of 1 sigma 1s, I just say 1 sigma. So the subscripts are omitted just for clarity and to save space. Okay, in the same manner, we can move on to the next one, which is the C2 dimer, the carbon dimer. In this particular case, our atomic number is 6. So the total number of electrons in the dimer is 12, 2 more than in the case of B2. So it's quite easy to figure out what's going to happen. In the case of B2, the last 2 levels, the 1 pi x and 1 pi y levels, contained only 1 electron. Whereas in the case of C2, those 2 levels will take on 2 electrons each. So there it is for the carbon dimer. So 1 pi x2, 1 pi y2 are the valence molecular orbitals. And I've omitted the stuff in the square bracket, but it's exactly the same as what we have for B2. And likewise we can do for the other cases. It's a simple matter of keeping track of how many electrons we have and where we place them. So there it is, the results for all of the 5 cases, and it's a simple matter of, as I said, keeping track of the total number of electrons in the system and where you place them in our molecular orbital diagram. One thing I want to note is that O2 is known to be paramagnetic, right? It is known that O2 has unpaired spins, and but you see, O2 has even number of electrons. So for a while it was hard to understand why O2 would display paramagnetism. Now the molecular orbital picture description of the electronic structure of the O2 clearly shows why O2 should indeed be paramagnetic, why it should have unpaired spin. So you see, so here is the electronic structure for the O2 system, and you can see that although overall you have even number of electrons, in which means that you expect them all to be spin paired, they are not really spin paired because of the pi levels. You have two electrons which you have to place in two equivalent degenerate pi orbitals, and so you have to place one in one of them and the second one in the other, and so you have two unpaired electrons. So this actually explains the paramagnetism of oxygen. Okay, now let us go to our third column, which is this. We can very easily figure out the net number of bonding electrons, right? Is the total number of electrons in bonding orbitals minus the total number of electrons in the antibonding orbitals. So there we have it. It's a simple listing of the net number of bonding electrons for all 5 cases, and of course we have made a definition of the number of bonds based on this net number of bonding electrons. And if you recall, you will realize that the number of bonds was defined as half the number of net number of bonding electrons. So let's write that down as well. So I've indicated the number of bonds for each case in red in brackets. And you can see that this is all very consistent with intuition. We know that fluorine dimer has a single bond, and the oxygen dimer has a double bond, and the nitrogen dimer has a triple bond, and those are indeed the results that we have obtained using our simple formula for the number of bonds. And it is also known that N2 is a very strong molecule. In fact, it is known to be the strongest homonuclear diatomic molecule. And let me just write down the values of the bond energy for each of these 5 cases, and we will indeed see that N2 has the highest value of the bond energy consistent with our notions. So there it is. You can see that N2 has the largest bond energy, and here are the bond lengths. And consistent with our 3s rule, N2 also has the shortest bond length. So it is the strongest bond, and it is also the shortest bond of at least these 5 cases. In fact, we can graphically show the persistence of this 3s rule. Let me do that very quickly. So this very simple plot shows the same information we showed in the table up above. So the net number of bonding electrons is plotted as a function of the species, as a function of the molecule. B2 has 2, C2 has 4, and so forth. And you can see that it peaks at around N2. Now let us make similar plots of the bond energy, the bond length, and the stiffness. And here they are, and you can tell that shorter bonds are indeed stronger and stiffer. I did not provide you the stiffness values in the previous table, although the bond length and bond energy values were provided. You can always look up the stiffness values of these 5 homonuclear diatomic molecules, and you will see that indeed this is the behavior that's seen. What we have seen so far is that the quantum mechanical picture of the behavior of electrons in atoms and molecules provides us with a very satisfactory picture. We are able to explain why fluorine is viewed as having a single bond, the fluorine molecule is viewed as having a single bond, whereas the nitrogen molecule is viewed as having a triple bond. We are able to explain why O2 displays paramagnetic behavior. We are able to also explain why N2 is one of the strongest diatomic molecules and the strongest homonuclear diatomic molecule with a rather short bond length, and so forth. So the quantum mechanical picture is rather satisfying and satisfactory, and we would like to take that further to the next level. And what we're going to do now is to move on from two atoms to many atoms. Towards that end, we are going to consider lithium, which has an atomic number of 3. So its atomic configuration is 1s2, 2s1, and we are going to ask the question as to what happens when we put lithium atoms together. First the dimer, then the trimer, and then the tetramer, and finally the lithium N system, where N is a very large number. We are going to attempt to draw the electronic structure of these lithium systems, and we will also attempt to draw the wave functions, the molecular orbital pictures of the various energy levels that we will encounter. So that's the next goal. As I mentioned, lithium has an electronic configuration of 1s2, 2s1, but we will ignore the core 1s2 states, as they will not really contribute to the emerging picture of bonding. So we will focus mainly on the 2s1 electron and the 2s state, and we are now going to draw the electronic configuration, the molecular orbital diagram for the lithium 2 dimer first. So there it is. That's our molecular orbital diagram. In this particular case, I'm showing only one set of atomic orbitals, right? Only the 2s level from one of the atoms. In previous pictures, I showed the 2s levels due to both atoms of a dimer. But again, for clarity and simplicity, I'm just showing one set of atomic orbitals. And of course, the molecular orbitals are labeled as 2 sigma and 2 sigma star. And in this particular example of the lithium dimer, the 2 sigma state is doubly occupied, because you have dimers, two atoms, 2 lithium atoms. Each one comes with one 2s electron, and so you have a total of 2 electrons that you need to put in the 2s level. Okay, so let's do it for the trimer now. So here is the picture for the lithium trimer, or Li3. So you have 3 lithium atoms coming together to form a molecule. Each lithium atom is coming with a 2s level that is singly occupied, right, as before. Now, because of the conservation of energy levels, you will have 3 levels in the molecular orbital diagram. Each lithium atom is coming with one 2s level. There are 3 such lithium atoms, so the total number of levels in the molecular orbital picture has to include 3 levels, which is why you see these 3 levels, 1, 2, and 3. You have 3 electrons that you need to place in these 3 levels. You start from the lowest, you place 2 electrons here, and then you have 1 here, and then of course that is empty. So that is the situation with the lithium 3 trimer. Before we move on to the more complicated cases, we are also going to very quickly make plots of the orbitals themselves, just like we did before. So here they are. So here is the how the wave function of the molecular orbital of the 2 sigma bonding combination will look. We have already seen this before. So there's accumulation of charge in the bond center. Likewise, this is the picture here for the molecular orbital corresponding to the 2 sigma star antibonding orbital, and of course there is a depletion of electronic charge at the bond center. In fact, there is a node. So we have already seen this before. We're going to make analogous plots, similar plots for the lithium 3 trimer now. Okay, so let's take a look at these 3 molecular orbital pictures. Let's look at the bottommost one, which is easiest to understand. That corresponds to the bonding combination of all 3 of the lithium atomic orbitals, the 2s orbitals. So because it's a bonding combination, you have accumulation of charge density at the 2 different bond centers. Note that, of course, these 3 dots here are the positions of the 3 lithium atoms. And at the bond center corresponding to these 2 atoms, there is accumulation, and likewise in the bond center corresponding to these 2, there is accumulation, which is what makes this orbital low in energy and bonding through and through. Now the highest level here is the antibonding combination of the three orbitals, which means that at any two bond centers, you have a depletion of charge, charge density going to 0, node, etc., etc. So this is a antibonding combination of the three 2s orbitals through and through. The middle one here is what is called as a non-bonding contribution. So the node actually here goes through the central atom. So it's neither bonding nor antibonding, it's somewhere in between. And by the way, I'm drawing these pictures without proof. One could make symmetry arguments, and one could also do a rigorous solution of the Schrodinger's equation to prove that these are indeed the correct solutions to these problems. Let me also make another observation, right? If you go back up here, over here you have a one node in the wave function. If you go to this case here, there are 0 nodes, right? There is no point in the region between the two atoms where there is a node. So there are no nodes. Whereas if you go to this case over here, here you have 2 nodes, here you have 1 node, and here you have 0 nodes. So I'm just going to make a note of these things. So there it is, and I'm sure you see a pattern here, right? For the first case, you're going from 1 0, and then the second case you're going from 2 1 0, and you know, as you increase the number of atoms in your lithium cluster, you will have a certain number of wave functions. In fact, if you have n atoms in your lithium cluster, you will have n different levels like this. Each one will correspond to a wave function like that, and of course the number of nodes will be different. So if you have n atoms in your lithium cluster, you will have wave functions with nodes going from n minus 1 to 0. And so we are going to demonstrate that a little bit further. We're going to consider a lithium 4 system, and then of course we're going to jump straight from there to the lithium N system, where N is a very large number, meaning we have reached the solid state. Okay, so let me give myself a little bit room. Okay, so there is a lithium 4 system, 4 atoms, 4 2s electrons, 4 2s states, and so you have 4 molecular orbitals, which have to now be populated with 4 electrons, right? So the bottommost 2 will be doubly occupied, and you'll run out of electrons at that point. So that is the electronic structure. This is the electronic configuration of our lithium 4 tetramer, and these are of course the pictures of the wave functions associated with those energy levels. The bottommost one is a completely bonding combination through and through of all 4 2s atomic orbitals, and the next one contains some bonding combination, some another piece of bonding combination, and then there is an antibonding combination over there, leading to one node. You see, the first case here has 0 nodes. This wave function here has 1 node, and the next one, higher in energy, also has some bonding aspects to it, but there is a 2 nodes. There are 2 nodes over there. And so that has a fair amount of antibonding combinations, which is why it is higher in energy. And the last one has antibonding combinations through and through with several nodes. In fact, 3 nodes. So you got number 3 over there. So you see this pattern. So you have a number of wave functions. If you have n atoms, you'll have n wave functions, and they will all be distinct in terms of the number of nodes that they display. So for the case of lithium N, I'm not going to, of course, be able to draw all the wave function pictures, especially when N is very, very large, and so I'm going to show it in a schematic manner. First, the electronic structure, the electronic molecular orbital diagram, which is what is shown over here. You have lithium N, where n is a very large number, so you have of course a very large number of electronic levels, and half of them are full. because by the time you reach this level over here, you have run out of electrons. So half of these many electronic levels are occupied, and the other half over here are empty. Okay, so what about the wave functions? Of course, there are going to be n of those, and each one will display a different number of nodes, ranging from 0 to n minus 1. In fact, the wave functions can be labeled based on the number of nodes. This is what we had attempted to do for the simple examples of Li2, Li3, and Li4. The wave functions can be labeled in terms of the number of nodes. In fact, the k vector that we've been discussing in the past within the context of omega versus q or omega versus k diagrams really can be used to label the wave functions. Here is an alternative representation of the same information that we are showing over here. And in this representation, we are plotting E as a function of our k. Each value of k in the x-axis of this plot, of the second plot, represents a different wave function. And we just saw that our wave functions can be indexed based on the number of nodes that they display, and in fact this is exactly what k keeps track of. So one way of looking at this mysterious reciprocal space quantity k is to just look upon it as a bookkeeping device. There are a lot of wave functions, and they have to be kept track of. One way to keep track of them is by noting down their nodal structure, or the number of nodes, and k helps us with that. The moment we realize the equivalence of these two pictures, the one on the left and the one on the right for our lithium N system, the mystery surrounding band structure plots is somewhat lifted. We note, of course, that the plot on the right, namely this one over here, is essentially the band structure plot for our hypothetical lithium solid. Each energy level on the left is indicated by each of these energy values in the plot on the right, and the wave function corresponding to each of the energy levels is, of course, indexed by our k values. So, in the case of our lithium N solid, when N is a very large number approaching infinity, we have a continuum of energy levels, which is represented on the plot on the right as this band. And since half of these levels are occupied and the other half empty, we have our Fermi energy over here. So, this part of the band is occupied. These energy levels are unoccupied. The Fermi level thus cuts across our band, and the Fermi level is over here. And this makes our lithium solid a metal. Of course, we note that we've made several assumptions, simplifying assumptions over here. We've assumed that each lithium atom is contributing a 2s orbital, and these n 2s orbitals combine together in n different ways, creating our wave functions and hence our band and the band structure. Had we included the 2p orbitals as well, we would get additional bands which would lie higher in energy compared to our 2s derived band. This is our 2s derived band. So the 2p derived bands would lie higher in energy, separated by band gaps, of course. In this discussion, we have implicitly assumed that our 2s atomic orbitals would combine to create a 2s derived band, and likewise the 2p atomic orbitals would create 2p derived bands, and the bands are separated from each other by gaps and so forth. In the general case, however, the s and the p orbitals, atomic orbitals, could mix with each other, creating bands that are actually mixtures, right? And such bands would display a lot of features, more features than what you are seeing in this picture over here. And that is what results in the richness of the band structure plots that you may have seen for many different materials. But we will get to all of that eventually. At this point, you should have a qualitative understanding of the electronic structure of atoms, molecules, as well as solids. Solving the Schrodinger's equation for atoms will lead us to atomic orbitals such as 1s, 2s, 2p, and so forth. Solving the Schrodinger's equation for molecular problems would lead us to molecular orbitals, which can be viewed as combinations of atomic orbitals. And finally, a solid may be viewed as being composed of an enormous number of atoms, and the solution of the Schrodinger's equation for such a situation, for such a solid, would lead us to an enormous number of energy levels and an enormous number of wave functions, which can all be arranged and organized based on the nature of the wave functions. For example, the nodal structure of the wave functions. Such an organized arrangement of the energy levels of our solid is what we call as the band structure. In the subsequent lectures, we are going to add more rigor to all of these qualitative notions that we have arrived at, and we are going to understand and appreciate the band structure of solids at a more deeper level. Thank you.